Okay, so yeah, so this is a lot of stuff. I followed your cue of putting an outline up. I like that. I think a lot of people have been doing that. Anyways, I'm gonna. Pardon me? Okay, I wasn't here for that. Anyways, I'm going to try to give you an overview of proof complexity, but I want to focus on some things that people don't usually talk about. So I want to tell you about proofs as games to try to motivate why it's interesting and you don't have to know any logic. However, then I'm going to tell you the logic view, which I think is actually pretty important and kind of unifies lots of different things that you might have thought of as different if you ever thought about it, or if not, then you'll have my view. Okay. So the standard definition of a proof system, what's now standard, is called a Cook-Rekoff proof system. And it's not the typical definition. The typical definition is, you see a bunch of rules and axioms, and we'll get to that in a minute. But this is a very general definition, which is just a Cook-Rekoff proof system is just an algorithm or a function A that takes strings to valid. Valid means is encodings of valid formulas, propositional formulas. So formulas that are true under every truth assignment. Okay, and you can assume that they're all DNF formulas if you want formulas. If you have any questions, I'm going too fast, too slow, just interrupt me. Okay? So you can assume that these are just DNF formulas, disjunctive normal form formulas, over variables x1 through xn. There's an easy reduction to go from an arbitrary valid formula to an equivalent one that's in this form. Okay. So this is an algorithm that takes strings, which you should think of these strings as encodings of proofs, to encodings of valid formulas, and it should have the properties, so the completeness, and the algorithm should be polynomial time. So in other words, you should think of these as encodings of proofs, and A is a verifier that's checking whether or not this encoding is a valid proof, and if so, it spits out what is a proof of. Okay? And completeness of the proof system means that for every valid formula encoded by tau, that there exists a string alpha such that A of alpha equals tau. So in other words, completeness means that A has proofs of every valid formula. Okay? And you kind of get soundness for free because the range here is all the valid functions. So that means you're never going to think you have a proof of something that's not valid. Okay?
And the length of alpha?
Right, good. So A is polynomially bounded if for every valid formula tau there exists an alpha such that the size of alpha is polynomial in the size of tau such that A of alpha equals tau. Okay, so we want proof systems, we'd ideally like to have proof systems where for every valid formula tau there's a short proof, okay, where the proof has length polynomial in the size of the DNF. Okay, and if such a proof system exists, so this is an easy lemma or theorem. So there exists a polynomial bounded proof system if and only if NP equals co-NP. Okay, so you can think of this. So what is going on here? The set of all valid formulas that's a co-NP property. Okay, so if you have a polynomial time verifier, then you have an NP procedure for a co-NP complete problem. You just guess the short proof and verify it. Okay.
So there's no polynomial.
So we think that there's no polynomial bounded proof system. Okay, that's the common belief. I'm not really so sure it's believable, but that's a different story. But today I'm going to tell you about specific proof systems that people study a lot. Frege systems, they're standard rule-based systems where you start with some axioms and some rules, and they can be algebraic, they can be more propositional. They're all very easily, the propositional ones are all very easily seen to be polynomial verifiable, we'll see that the algebraic ones, sometimes they're only verifiable in probabilistic polynomial time. So they lie, well, we think that there should be polytime verifiers for them under assumption that you can do polynomial identity testing in polynomial time. But at the moment, a lot of the algebraic ones are just polynomially verifiable. But we'll get to that later. Okay, so what we're going to do is study, real proof systems. Ones that people study are much more restricted. They usually follow some specific set of rules. So, a proof is usually like a sequence of lines where each line is either an instance of an axiom or follows from previous lines by one of the rules, and the last line is the thing you're trying to prove. That's typically what they all look like, okay? And the two things I want to try to drive home or convince you of is that by studying specific proof systems, so two things I want to focus on are so specific proof systems, specific systems, lower bounds for them basically rule out large families of polynomial time algorithms for NP hard problems and even approximate versions of them. Okay, so we know that if you can show that no proof system is polynomially bounded, you've basically ruled out every algorithm. So you've proven, not only have you proven P not equal NP, but you've proven NP not equal co-NP. But I want to say that for specific proof systems like Frege systems, like sum of squares, systems that people study, the reason people care so much about them is because most of the algorithms that pretty well all the algorithms that we know of that have correctness proofs, so we know that they're valid, that they're good algorithms, all of those algorithms, kind of the correctness proof lies in some proof system, so it can be proved in some proof system, and therefore lower bounds in that proof system rule out a large family of corresponding algorithms. Okay. So that's one point I want to make. And the other point I want to make is that these proof systems, these specific ones, or almost all of them, have a dual form, a dual characterization. So it's like so all of the proof systems that we'll talk about, they have like two views. One is like the syntactic view, where I'm going to tell you there's a bunch of axioms, and I specifically tell you what they look like, and that's what the A is going to verify, that it looks like that. Okay, and then the dual form will describe if you don't have a proof, then there's some model. Okay, and the model in the algebraic case will be the pseudo distributions. In the propositional case, I won't have time to really fully spell it out, but they're it's a model, more of a logical model theoretic type of construction.
So there's no condition on what this algorithm should do. It could just do whatever it wants.
That's right. So the thing that's kind of very disconcerting is that a propositional proof system could even be like Zermelo-Fraenkel set theory with axiom of choice, like anything you could conceive of that's sound incomplete. And it's it's verifiable, and it works with way more complicated formulas than just propositional ones. But as far as we know, we don't have any idea whether that's even more powerful or not for just normal propositional statements. So it's really a kind of a conundrum.
But there's no condition that says an algorithm should do something sensible. Like at the moment, it just looks like a map between two things, and it's something that you do polynomial time.
Well, I'm forcing it to have range the valid formulas. So for example, you should think about some strings are going to be legal encodings of proofs. The illegal ones, what are we going to do with those? Well, typically they'll map to some trivially valid formula like X or not X. Okay, so it has to be somewhat sensible.
Propositional means what? That it has no quantifiers?
Pardon me?
What does it mean that the formula is propositional?
Oh, I'm sorry. So propositional formula is just, so the standard one is over binary and or not. In variables, the variables are formulas, and if, so like inductive definition, if F is a formula and G is a formula, then that's a formula, and that's a formula, and not F is a formula.
But no quantifiers.
No quantifiers. Yeah. So, and a DNF formula would be like x1, x2, or x1, x2, or try to make this true, or x2, something like that. So that would be a valid. Good? Okay. Okay, so I'm going to first tell you about, I think that's about it for what I wanted to say in general. If you have any questions, there's tons of open problems. I mean, we don't know anything, essentially. I'll tell you the little bit that we do know. There is this very strong relationship or analogy between circuit classes and proof systems that I'll get to, which is you can define a proof system that's allowed to reason about formulas or functions from a certain circuit class, okay, and then that's sort of analogous to that circuit class. So the standard one is you're allowed to reason with polynomial size formulas. So formulas where the size of the total number of connectives is polynomial, and we think of that, that's the standard Frege system, where you have some specific set of rules for it, which I'll give you an example. And that sort of corresponds to the complexity class NC1 or formula size, polynomial size formulas. But we certainly don't know how to go from lower bounds from the circuit class to lower bounds for the proof system. But we have no real good connection in either direction. So it's okay. So proofs as games. So any questions so far? No, I'm going to be much more specific. So a proof as game, there's two players. And these were defined by, it sort of falls out of, there's lots of like normal form theorems for proof systems, and which I'll tell you about. And when you kind of get used to those normal form theorems, this kind of falls out. But it's very nice to sort of think of them this way, because it's simple. You don't have to know anything about the rules or whatever. But I think it's a little bit misleading to not know a little bit more. So I'm going to tell you a little more. But I'll start with proofs as games. So I want to try to convince you that this is actually that propositional proof lower bounds for standard Frege systems is a very clean problem. So that's what I want to convince you of. So you have two players. You have a prosecutor. And prosecutor is trying to, prosecutor thinks that, so you have some formula F that's valid. So it's true under every assignment to the variables. And you have two players, the prosecutor who is claiming that F is valid, and the defendant who's claiming that F is false, that there's a falsifying assignment. So for example, maybe Avi is the prosecutor, and he says that Tony stole the lunch card yesterday. And I'm saying there's a scenario where I didn't. Okay. So this is just for fun. So maybe Avi asks me, so what's going to happen is there's going to be a dialogue between the prosecutor and the defendant, and the dialogue takes the form of the prosecutor asks yes/no questions in the form of formulas over the variables x1 through xn, and the defendant answers the questions. And it should be the case that at all of the leaves, so you're going to make a tree, okay, with these yes/no questions, and at all the leaves of the tree, the prosecutor should have forced the defendant into a blatant lie. And a blatant lie is going to mean that there's going to be a violation of the truth table definition of one of the connectives. So in other words, I'm going to either be forced to say A or B. For some A and B, formulas A and B, I'm going to be forced to say that A or B is false, but I also said say that A is true. Okay? So maybe Avi asks me, this is just a simple example, did you steal the card? And here's I say yes, and here's I say no. And yes, Avi says, aha, so you did steal the card. And no, then he says, did you lie? And this is a typical liar's paradox. Here he says, yeah, you lied, so I'm not even going to deal with you. And no, he says, so you're a liar. So but let me give you a real example, okay? So by real, I mean like an more interesting example, which is induction. So this is propositional induction. It might look it's like might look a little different than what you're used to, but it really is the same thing. So if x1 is 1 and xn is 0, then there exists an I where xi is 1 and xi plus 1 is 0. Okay? So to say that with a DNF formula, we'll say either x1 is 0 or x1 is 1 and x2 is 0, or x2 is 1 and x3 is 0. When I just do them like that, it's an and. Okay? This is like x1 and negation of x2. I'll do a few more. So that's induction up to n equals 5. Okay? Okay, so it's valid. And so now we want to come up with a sorry, I want to say one thing. So what do I mean exactly by a truth table definition? So I'm going to be, just so we don't waste time, I'm going to be a little more liberal with, I'm not going to just have binary and an or, but I'm going to allow arbitrary fan-in and an or. So the truth table, so if I have like formulas A1 through AK, this is the truth tables. So you can think of the and of size 2 if you want, but
So you said that bad proof should not go through in this, right? So if the defendant is actually lying, then you can force.
That's right.
So what about the good proof? How do they?
So if this is not valid, then you won't be able to succeed. Is that what your question is?
So is this only for catching bad proofs?
No, so yeah, good question. So if you start with a valid formula, it is always possible to come up with a game where the prosecutor always wins. Win means that you can come up with a tree, you know, where you query formulas at all of the nodes, and at every leaf, if you look at the formulas that you queried on the path to this leaf, there's an explicit truth table violation for every such. I'll give you an example now. At every such leaf. So a formula is valid if and only if such a thing exists. Okay? If it's not valid, then there's a falsifying assignment, and then the defendant will just actually be honest, right? And follow the path that's consistent with the falsifying assignment. Okay. And what we're going to measure, the complexity measure, is going to be the height. The complexity measure of the game is going to be the height of the tree. So that's it. That's what's so nice about this. You don't have to worry about the formula size or anything. Okay.
So a trivial tree is if you say, is this a satisfying assignment? Is this a satisfying assignment? Can you just run through all the assignments and ask if
yeah, I think an easier way to do it is to make a tree where you ask about x1 true false, x2 true false. Okay. That's the short proof that always works. And then you have some work to do at the leaves to actually get the contradiction sometimes, you know, tiny bit of work. But you'll always get a truth table violation that way. Yeah, because you know that one of these terms will always be true. So then you'll get a truth table. You know, then you have to query the term that actually was set to true by that assignment. and then you'll be done.
Okay. So linear size is
No, the height will be linear, and the size will be exponential. Yeah, so we're going to see that the size of a Frege proof is going to be pretty well exactly 2 to the height of this game. Okay, so again, I just don't want to waste my time, so I'm going to just do, I don't want to have to deal with the fact that if I make one of these terms true, then I'm going to have to like query, you know, do all these queries. So instead I'm just going to be a little more liberal with the truth tables, and you know, if any one of these is 0, then this is 0, and if all of them are 1, sorry, that's not meant to be a star, then it's 1, and likewise for the or the other way around. So if one of them is 1, if you have any 1 anywhere, then it's 1. And, and if you have all zeros, then it has to be 0. Okay, so you automatically get a truth table violation if you have a 1 here and this whole thing is 0. Okay, and negation is just okay. Okay, so how would I do this? So we could do what you said. We could just query them x1 through x5, but that's not going to be the shortest proof. It'll have height. You know, you can always do height linear in the number of variables. So what would be a better strategy?
Bisection.
Yeah. So the better strategy is like, you know, make sure this is 0 and whatever. Make sure this is 1 and this is 0, and then cut in the middle and see which way to go. Okay, so we would go like, first we'd query x1, and you start off kind of knowing. So if this is f, you start off knowing or assuming that f is 0. Okay. And so here we query, you know, x1. Here's x1 equals 1, x1 equals 0. Okay, and so when x1 is 0, then this is true. So we already have a truth table violation. Okay, so here we're done, and we sort of violated the truth table for f. Okay, and when x1 is 1, then I'll query x5. Let me know if I make a mistake, because I usually do. I'm not good at okay, so when x5 is 1, again we get a truth table violation to f. And now when x5 is 0, now we have our endpoints that are, you know, both 0. And so now we're going to cut in the middle. In the middle, I guess, is x3. I'm going to run out of room. And so when I set x3 to 1, so nothing's happened yet. I haven't forced anything to true. So when I set x3 to 1, what do I want to set next? So when x3 is 1, so I guess I want to set x2. I think that's right. No, let's see. No, I think I want to set x4 then. Okay, so when x3 is 1 and x4 is 0, then this has been made set to true. Okay, so I'm going to do this path now. So now I have to actually now query x3 and x4 negation. Sorry, I'm running out of room here. So here I've set x3 to 1, x4 to 0. So I've made this thing true. Okay, so in this path, that's consistent. But now I've violated the truth table definition of f again, because I have a term that's true, but I said f was false. So here I can say I violated that. And on this side, I've now violated the truth table definition for this and, right? Because this one I said this was 0, but I said x3 was 1 and x4 was 0, right? So this, I violated x3 and x4. Does that make sense? And you can fill out the rest, right? Does it make sense?
So why was this better than the trivial?
Yeah, a little hard to see because such a small example. But since I'm doing it, when I did x3, so what I'm basically trying to do is go to one side or the other. So when I set x3 to 1, I queried x4, and when I would set x3 to 0, I would query x5. So it's like if you know, I have on the left that x1 is 0, and this thing, it's a little bit weird because I'm not doing the falsifying one, so I always get mixed up. Like normally you would say if the left one is 1 and the right one is 0, then there exists a 1, 0 somewhere. Okay, so you would query this bit, you'd query the middle one and then do binary search left to right. That's all I'm doing here.
Because of the specific formula.
Yeah, it's because it's specific. I can't do this in general. Yeah. Do you want to see more? Does this make sense, or should I keep doing it? Good?
So this tree has depth,
Like log n. Yeah.
like what's a constant?
Yeah.
And that's also lower bound, I guess.
Pardon me?
The that's also lower bound, like you cannot do better than nothing for this one, or no, for this
Yeah, I think you can always get a lower bound. I mean, if it really does depend on all the variables, then I think you always can do log n. Yeah, you can sometimes cheat if you have a very long formula where the tautology is just. Does that make sense? Okay, so this is like a kind of a simple, relatively simple strategy, because even though, the simple strategy is just query all the variables and don't even pay attention to the order. This is somewhat more sophisticated, but not that sophisticated. We're still just basically just querying variables, but in a smarter order. So this is really just like a decision tree that's finding the term that's violated. Okay, so this is not such a fancy strategy. So just to show you that there's fancier strategies, and the whole power of proof systems is that you can do things besides just query variables or literals. You can query formulas. Okay, in this case, we didn't need to do that.
Restriction here on how complicated the formula query.
No, that's what's interesting. So it turns out that if you try to query a really complicated formula, but the proof has shallow, then more or less there's so much of it you could never have even looked at. So you don't. So turns out that the size of the proof. So first of all, the proof can always be balanced. So you can always come up with one where the height is logarithmic in the size. And also it turns out that what you're querying, the formulas that you're querying, never can really be bigger than the size, because otherwise you wouldn't really need those connectors because you could never look at them.
So the best tree is a characterization of the complexity of the formula in a way?
Pardon me?
So the best depth is
Yes.
characterization. And can we get any exponent, for example?
Uh,
Can we, so we know it's going to be between logarithmic and linear.
yeah, I mean,
It
it's
shows that
pathetic.
For any alpha equals between 0 and 1, there's just a formula that has this exact scaling asymptotically for the
No, pretty well almost every question you'll ask me, the answer is no. The very best that we have lower bounds for is a 2 log n. And it's sort of it's not, don't think of it as like an n squared formula size bound, because that is non-trivial. But this 2 log n is more or less because if you work in the bounded Fanon 2 case and you come up with a dumb formula that's like, that looks like true implies true implies true implies something, like a dumb nested formula, like x1 or, and then in the very inside you put not x1. Then just to get there, just to get to the contradiction, kind of takes you n squared. So it's not, there's no real good, any non-trivial, I would say, lower bound.
Well, I'm not saying a lower bound, I'm just saying existence, right? Like
No.
just a counting.
No,
argument.
there's no
Like
counting
there's
arguments.
lower
There's
bound.
no counting argument.
Okay.
So I mean, obviously there's no counting argument for NP versus co-NP, but even here we don't know how to count valid formulas.
Okay.
So we don't know how to prove even non-constructively anything. Yeah. Yeah. Okay, so let me just show you. I mean, you do proofs all the time, so you shouldn't be so surprised that you can do something besides just, query variables. But the pigeonhole principle is probably, the most common example of a propositional formula where there's a natural proof that's short that queries formulas instead of variables. So for a pigeonhole, you want to say that, that any mapping from n plus 1 pigeons to n holes has to either leave out, well, either it's not a mapping, it leaves out a pigeon, or at least 2 pigeons go to the same hole. Okay, so the variables are Pij, where I is in n plus 1, and j is in n, and you have, this is pigeon I term, which is saying that either pigeon I doesn't go to hole 1, the pigeon I doesn't get mapped anywhere. Okay, so this says pigeon I not mapped. And then we have whole axioms, H, I1, I2. I'm just going to leave out these commas, J. And this says that these 2 pigeons map the whole J. Okay, Okay, they both map to whole J. And then the pigeonhole says that or over I in n plus 1. So either some pigeon gets unmapped or some two pigeons, I1 and I2, map to the same whole J. Okay, so that's the formula. And it's a family of formulas, one for every n. And the size of it is something like n to the third, and the number of variables is, something like n squared. So it's all polynomial in n. And so what we'd like is a proof whose height is logarithmic in n. Okay. So we do know that if you just query variables, so if the strategy just queries variables, then it requires exponential size or linear height. Okay, you can prove with a fairly simple adversary strategy that the height has to be linear if you just query variables. But how would you actually prove this to yourself? I mean, you wouldn't do that, right? So I think what you would do is, so if you're the defendant or you're the prosecutor, 1, 2, 3, 4, 5, 6, 7. So this is n plus 1. And this is n. So how would you actually try to get the person into a lie? Any ideas?
Are there less than n over 2 pigeons?
Exactly. Exactly. Yeah, so you'd ask questions like, I don't know if it's worth me writing down, but you'd ask like, just what you said. You basically say, all right, what is the count? Like, I'm going to start a step back. Just make sure that the count is, the count is either going to be at least n plus 1, or the count's going to be less than n plus 1. If the count's at least n plus 1, then you know that there has to be a whole violation. So you're going to start focusing on the count of the edges coming into the first half versus the second half, and zoom in on the whole. Otherwise, if the count is at least is less than n plus 1, then you know that some pigeon didn't get mapped anywhere, so you'll start asking about the count of the edges coming out of the first half of the pigeons, and you'll zoom in on the specific pigeon that didn't get mapped. Does that make sense? So I could do it, but it actually takes some time because you have to actually come up with a formula that counts, right? So a formula that takes as input some number of variables, at most n squared, and the output is 1 if and only if the count, so a formula that, exactly what Daniel said, that takes as input some number of variables and outputs 1 if and only if the count is bigger than or equal to some k. Okay, so you have to write down some formula for that, and then when you zoom in on this thing, when you finally get to the point where there's a violation, you actually have to then, you're going to basically be violating something about your circuit, the correctness of your circuit, right? Like it'll be specifically you'll have, let's say that the count of the whole thing, say the count of all the edges is less than n plus 1, okay? And then let's say let's call this h0, the first half, and let's call this h1. So then you'll do the count of the edges coming into h0, and let's say that this is less than size of h0. This is either less than size of h0 or bigger than size of h0, okay? And likewise, the count of h1 is either less than size of h1 or bigger than or equal to the size of h1, okay? And the count of all the edges, that's the count of h, so this whole thing. So it's less than, I said the count of this is going to be bigger than n. Okay, so I'm doing the case where I counted them all. The count was, n plus 1 or bigger. Okay, so then I was trying to zoom in. So you're going to ask about this count and this count. What's going to happen? Well, you try to zoom in on this. One of the two has to be less than, since this is bigger than n, one of the two has to be bigger than its size. But you have to actually prove that. If that doesn't happen, so there's 3 possibilities, right? One, you can actually keep going because h1 is, the count of h1 is too big. So then you're going to do divide and conquer on that. The other one is the count of this one is too big, so you'll recursively continue on that. In the third case you have to deal with, which is that the person says, oh, well, you know, the counts match up, even though they don't, right? That the count of the whole thing is n plus 1, but this one is, you know, is as small as it should be, and this one is as small as it should be. So at that point, you're going to have to delve into your addition circuit and find the mistake. Okay, so that's why it's a little hard to write it down.
So it's a less equal and greater than.
Yeah, did I mess something up? I think
Equality was on the other side.
here.
Yeah.
What did I do wrong? Say it again.
Should we have it?
So you want the less equal to and greater than it, so because otherwise it will not, I mean, it can still be equality. So the two cases will be like it's either less than equal to the size or it's bigger than the size.
No, I want it to be less than the size, because if it's less, I mean, it's
Or then you go to the other side. Okay, if it's less
yeah,
than
here. So I'm going to start off with the count. Oh, it's good? Yeah. So I'm just saying that there's, you know, the easy cases where you're going to just recursively continue is when the person is not lying about the count. In other words, they're always going to be consistent with, you know, if the count of h is n plus 1, let's just say it's equal to n plus 1. Okay, then the counts that it's going to come up with for these are going to match this. So some of them is going to match that. Okay, that's when the person's not lying about the count. In that case, you just recursively continue, catch them in a lie. The hard case is when the person says this count is n plus 1, but this, you know, one of the two, but each of these two is exactly h0 and h1. So some of these two don't match. Some of these two will be n, but this is n plus 1. So in that case, you have to actually, like I said, go inside your formula that's supposed to be counting and find the mistake. Okay, and you can do that in logarithmic depth, logarithmic in the formula size. And there's counting formulas that are polynomial size. So that third case, which is the hard case, won't add too much to the depth. It's just, again, it's going to be a binary search to find the place that they made the mistake.
So I have some sort of a
Yeah.
mental disagreement with what's going on here, and I feel like I would want to, if I were to come up with this, I would want to limit the complexity of the formulas that I can query, but somehow you seem that this takes care of itself, because if I put an exponentially long formula, I'm going to get too far from my truth table, and then I'm going to have to come back to it. But is there intermediate results where I say I force myself to use formulas that have length, like, I don't know, let's say if I use only polynomial length formulas, or even, I don't know, constant, right? So the first one only had a constant number of variables in each formula. Here we start having linear number of variables in each formula. Does that lead to gaps in terms of the depth of trees?
Yeah, so you can prove, it's maybe a little hard to see, but you can prove that if you have a legal game that has a certain size, then all of the queries are no bigger than that size.
No, the other way around. If you say you bound the size of the formulas to be constant, then do we know how to prove?
No, so the case of single variables, that's, you know, the queries are just variables, and so if they're single variables, we know how to prove a lower bound, but it's not always the case that it's small just because the queries are small. Is that what you're asking?
And if you knew every formula that you query was only length 10.
Right, like variables is length 1.
Right. But
So-
that's the same as saying 10 variables maybe. And
Right,
so
because
you can
like
get
in the first
trivially-
example, the induction one, we used 2 variables per query, right?
No, we used more than that, but anyways, like log. So each query was 1 variable until we got to the end. I'm ignoring the stuff at the end. Yeah. So you're right. At the very end, and in general, you'd be querying. I'm not sure I'm answering the question. So I think when we get to the sequent calculus, it'll make more sense. But in general, you're going to have to query, if it's very small things that you're querying, like literals, you're going to have to query the same literal in general. I mean, not always, but in general, you're going to have to query the same literal many, many times. So the proof is, you know, that the length could be linear and the size could be exponential. On the other hand, you can't query formulas. You don't ever need to query formulas that are a lot bigger than the total size of the total number of nodes of the tree.
But you mean this is intermediate case where the formulas are at most length, you know, 5 times
Right,
10 or something.
right,
and
yeah.
Then do you know no?
Nope. No, the only thing we know is the best thing that we know is that if you can restrict the queries to be bounded depth in AC0 circuit queries, so where the queries are, let's say, some fixed depth where n goes to infinity. So for Pigeonhole, the best lower bound, this is the best lower bound that we have. So for the Pigeonhole principle in particular, is n goes to infinity. If you restrict the prosecutor to ask bounded height queries, and you can make it even height log n, then the any strategy has to have linear height. I think it's.
And are there any setups where we restrict the prosecutor's capacity, like we're doing it now, where we get lower bounds that are not jumping from logarithmic to linear, but jump, say, to root n?
Don't know anything else.
Okay.
Yeah. Yeah, it's amazing how much is open here relative to what's known in the circuit world, and even in the algebraic circuit world. Okay, is it good so far? Do you need a break, or can I keep going for a little? What time is it? Oh, I'll go for 15 minutes, then we'll take a little break. Okay. Okay. Oh, I wanted to show you the sequent calculus, which I wrote down. So, by the way, this lower bound for the Pigeonhole principle, it's fairly old. It was Itai originally did it in the language of non-standard model theory and got like barely super polynomial, and then my thesis, which is like very very old, proved the truly exponential bound. And I realize now, I mean, I did it not with non-standard models, but all combinatorial. But I kind of realize now that it's really important to understand the non-standard model point of view. So that's partly why I decided to talk about this today. Yeah, so I won't have time to do that lower bound proof, but
So your lower bound was the bounded circuit size?
yeah.
Okay.
Well, Itai did it like I said, his result is, I don't know, from 86 maybe, and then my thesis is, I don't know, 92 or 93, something like that. So it's old, and nothing's there's a recent result by Hofstede. Well, there's been some improvements. So this was super polynomial, this was exponential, but it doesn't. So to prove lower bounds for, say, counting or for parity for AC0 circuits, we have lower bounds of the form roughly 2 to the n to the 1 over d, the omega of 1 over d, for, say, parity or for counting. And the lower bounds here were like 2 to the n to the 1 over 2 to the d. So the depth, so if you wanted to maximize, get the best depth lower bound and still be super polynomial, it was, it wasn't so good. It was like log. And in Hofstede and a paper by myself, by Rossman, Tan, Servideo, and me, and then he improved on that, gets like more like this. And that's kind of like pretty well all that's known. There's a lot known for very weak systems like resolution, where you query literals. We'll get to that. Okay, so I do want to tell you a little bit about a standard proof system so that you can see a little bit why standard proof systems, which really aren't so bad, correspond to these games in a pretty natural way. Okay, so this is going to look ugly, I have to warn you. This is why people get turned off by proof theory. But I actually want to so it turns out that there was this, somebody put something on Twitter about the sequent calculus. I was going to wear my t-shirt. I actually got a t-shirt out of this. Somebody's like, does anybody know what the sequent, because I guess it's taught in Europe and it's very famous. I mean, it's like the proof system that's always studied. In North America, nobody knows about. So it went sort of semi-viral, and all these people started saying what they loved about the sequent calculus. And it kind of motivated me, because it really is the right system to understand, to unify propositional logic, first order logic, systems of bounded arithmetic, for a very simple reason, but it's really the right, starting off with the sequent calculus, the proofs of completeness, even for the first order systems in piano arithmetic, become extremely easy compared to the original proofs, which started with a different axiomatization. So along the line, I'm going to try to convince you that if you start with the right system that's kind of nice, that keeps all the connectives separate, that things are kind of flow naturally and it's not so ugly. Okay, so what's weird about the sequent calculus is normally you would just say, okay, lines are formulas, right? But now we're going to do something somewhat more complicated. Lines are going to be sequence. So a line in a sequent calculus proof looks like A1, comma, AK implies B1, comma, BL, I guess. And the meaning of this is not, it's not an implication symbol. It's like a symbol outside. It's a proof, I don't know what to call it. It's not a logical symbol, okay? But you should interpret this as the conjunction, as A1, the conjunction of the formulas on the left imply the disjunction of the formulas on the right. So that's what this means. Okay, now this looks weird, but it's very important that we don't write it this way, that we don't write, you know, A1 and AK implies, logical imply B1 or, okay. I know, it seems weird, but stick with me for a minute. Okay, so that's what lines look like, okay? But again, they have this natural interpretation, so it just looks a little weird right now. And then the rules, we're going to have one axiom. And the axiom is just for any formula A implies A, okay? And there's going to be some structural rules, like if you know that, so when I write gamma, gamma is just a sequence of formulas, and delta is another sequence of formulas. So again, you think of this as the conjunction of this stuff implies the disjunction of this stuff. And weakening just says you can always add anything to the left and or anything to the right. So if you already know that this stuff implies this, then you can always add something and it still implies this. And likewise, if you already know that this implies delta, then it's still going to imply delta or something else.
Sorry, what does this line mean?
So you should interpret this as the conjunction of these things logically implies the disjunction of this.
What is
Oh, sorry. This means from, so these are the rules. From the stuff on the top, you can conclude the stuff on the bottom. So this is like a rule schema. So if you have anything that looks like this, so a set of, a set of formulas on the left arrow, a set of formulas on the right, you can always weaken to add anything on the left and anything on the right. Okay, and another structural rule that I didn't write down, it's called contraction. If you have 2 copies of a formula on the left, you can replace it by 1 copy, 2 copies on the right. So you should think of this as sets of things. Okay. So what's nice about it is you literally have like one rule. You have rules for that correspond to the truth table definition of your connectives. Okay. So this is the binary case. You can easily extend it to the unbounded Feynman case. But for the logical rules for every connective, in this case I'm using and, or, and not. Those are my connectives that I'm going to be allowed to use to build out my formulas. For every connective, I'm going to have exactly one rule. It's going to introduce the connective on the left. So it's going to build up a bigger formula on the left with that connective, and another rule for building up a bigger formula on the right using that connective. And I'll have exactly one of these on the left and right for each of the connectives. Okay, and another special thing, and again, you need the sequent calculus for this, is something called the inversion property, which is going to be, so you want the rules to be sound. You want it to be the case that if you have an assignment that satisfies this, and it satisfies this, then it satisfies the bottom. You always want that. But inversion means it goes the other way around. So in other words, if you have something that satisfies the bottom, it's going to satisfy both of the top. Okay, and that's going to be really wonderful for us. You'll see in a minute. Okay, you don't need that for soundness, but that extra property of inversion, if and only if property, is going to make completeness very easy for us. Okay. So the and left rule is, if from A, think of this as A and B and gamma implies delta, then obviously I can just put A and B together. Okay. And the and right rule is if I can deduce A from some stuff and I can deduce B from some stuff, then I can deduce A and B from that stuff. Okay, does that make sense? See, it takes a little while to get used to it, but then you do the same thing for there's a corresponding or left and or right rule. And negation left is like you can always move something to the other side and negate it. So if you can prove A, that's the same thing as not A, is not A on the left. So not A implies nothing is the same thing as A. Is that good? It doesn't matter if you don't understand the details of the rules. What's really important is that, like I said, you have one rule for introducing each connective on the left and on the right to build up a bigger formula, okay, with that connective. And the rules are all sound. Sound meaning any assignment that satisfies this and this satisfies this, And you also have a property, this inversion property, that except for the weakening rule, everything has this inversion property, that if you satisfy the bottom, then you satisfy each of the top. So in other words, if the bottom thing is valid, both of the top things are going to be valid. Okay?
So if I go back to the, conjunction implies disjunction thing, I like completely described it with this set of rules, and in particular, right? So those are all things I could deduce just by telling you
Yeah.
that this arrow means that, right?
That's right.
And so the question is, did I forget something, and two, do I get the inversion from this?
Yeah, you could just do the replacement the way you did it, but this is the reason that we don't want to do it that way. This is called the cut rule, and this is the only rule that really has any power. Okay, these rules are just dumb, and they're more or less just like doing truth table things. Okay, this is really the whole workhorse behind the proof system, which is, if you wanted, let's say you want to conclude gamma implies delta. This is saying I can, out of the blue, come up with some really clever formula A, and if I can show that A implies, just for, you can always think of gamma as not even being there, because you can always push it on this side by negating it. So this is like saying, if from A I can deduce something, and I can deduce the same thing from not A, think of this as not A, this is the same thing. Okay, I can always move A, I can move A on the left by negating it. So it's saying if I can prove delta from A, and I can prove delta from not A, then I can prove delta, period. Okay, so this is like the power of the whole thing. In the pigeonhole proof, this is sort of what we did over and over. We had these counting circuits, and we were assuming something about the count, that the count of, whatever the count was is this, then I can conclude something. If the count is the other thing, then I can still conclude it. Okay, so this is really like where the power is coming from. And it's because of the cut rule that we really want to keep everything separate. Because we want to prove completeness, we want to not ever have to use the cut rule. It just makes things, it's a little hard for me to explain exactly. But if you tried to prove this yourself, starting with some other proof system, you'll run into trouble unless you kind of realize this is how you should have done it, and then do it this way, and then translate everything back. Yeah. Okay, so let me just show you completeness, because it's so easy that sorry about the noise. So by the way, this is called, the sequent calculus for propositional reasoning is called PK, and you can generalize it for first order, and then it's called LK. Don't ask me why. Somebody might know, but I don't remember. It's some German, it's German words that I don't remember. So completeness, we want to show that, if we have a formula, if F is valid, so it's satisfied, it's true under every assignment, then there is a PK proof, a sequent calculus proof of F. And I didn't really tell you what a proof was, but you're trying to prove F. So in the sequent calculus language, you want to prove arrow F. And a proof is just a sequence of sequence. These are called, this is very bad language, but sequent is what these things are called. Okay, sets imply sets. And so a proof is just a sequence of sequence where each one is either an instance of an axiom or follows from previous ones by one of the rules. Okay, and to prove completeness, all we're going to have to do is more or less, we're going to prove it in reverse. So we're going to start with the thing that we're trying to prove, and we're going to go backwards, okay, applying the rules in reverse. And it's just going to do the dumbest thing possible, which is just, take some outermost connective in F and apply the appropriate rule to break it up to get smaller things. And we just keep doing that until we're left with all literals. Bunch of literals, bunch of variables implies a bunch of variables. So you make this huge tree, okay, by just in reverse, applying the rules in reverse, the logical rules, just the logical rules, okay, breaking up the outermost connective. So you'll start with some F that has some complexity, you'll break up some outermost connective, and sometimes it'll just give you one sequent, sometimes it'll give you two. Okay, so here when I do it in reverse, I go from one sequent to two, and here I go from 1 to 1. So in general, I'll get this big tree, okay, and I stop whenever I have all just variables imply variables, okay? Make sense? Now, what do I know? I have inversion. So if this is valid, then everything down here is valid, okay, because, by induction. So what does that mean? That means everything down here has to have, the only way it could be valid down here is to have some variable that occurs, the same variable that occurs on the left and the right. Okay, so that has to be the case, because if not, then I can always find an assignment that falsifies that thing. That's it. That's the whole proof of completeness. I can do an example, but does that make sense? Do you want to see an example? Good?
So did you ever have to use the weakening?
No. So you don't want to use weakening for this proof, because then you won't have inversion.
So it's
Yeah.
completely
The only time you have to use weakening, and this is
very end.
exactly. So at the very end, you'll have x1, x2, x5 implies maybe x1, x7 or something like that. And then technically you have to do weakening to get to x1 implies x1. And in fact, you don't really have to go all the way down to the variable case. It's just the easiest way to prove it. You can stop whenever you have a implies a for any a. So this gives you the proof of completeness. It also gives you what's called cut elimination theorem, which is saying that for any valid formula, you can always come up with a proof that doesn't use cuts at all. Okay, it's going to be big in general, but okay. There's another proof of cut elimination that's the more standard one, where you actually start with a proof that has cuts and you get rid of them. And that's equally easy here, because you just, if you have a proof that has a cut in it, you kind of just replace it by its two pieces and use the appropriate rule. I'm not going to bother with that, but. So let me just tell you, briefly how we get the equivalence, and then. So I'm not going to do the proof of the equivalence, because it's it's not so interesting, but I'll give you the high level idea. So the theorem is that let f be some valid propositional formula, then the minimum Frege proof size, or PK proof size, and the size of a PK proof is more or less what you think it should be. It's just you just sum up the sizes of all the formulas in every line of the proof. So just sum up the size of each sequent. Okay, and so the minimum PK proof size for f is going to be equal to 2 to the theta of the depth, minimum Bus-Pudluck depth for the game associated with. So the depth really does exactly characterize the size. Okay, and the theorem is very general, the proof is very general. So, I set up the sequent calculus there, so it's for binary and an OR, but I could have changed the rules to be unbounded fan-in and an OR, and in that case, I would still get the same thing, but now the PK proof would have, only bounded, I could do the same thing for unbounded fan-in. I could restrict the depth, I could restrict the PK proof to only allowing cuts on, say, bounded depth circuits of unbounded fan-in, say depth D, and then the minimum PK proof size with that restriction is exactly equal to the minimum depth of the corresponding Bus-Pudluck game, where again you put the restriction that the prosecutor is only allowed to ask depth D queries. The formulas is only allowed to ask about circuits or formulas of depth D unbounded fan-in. And again, you can change the connectives, you can add mod p connectives, you can add threshold connectives, add the rule on the left and the right, and you get the same thing. Okay. So the high level of the proof, so one direction, if you want to see more details, I can give them to you, but I think you probably don't. But the high level of the proof in the one direction is if you have a game, why it corresponds to a PK proof. So the game to the PK proof is the easy direction. I wonder if I left that example up or did I erase it? Oh, good. I left it here. So I can just show you. So basically, all of these queries, they become applications of the cut rule. Okay? And then at the leaves, you have to do a little bit of work with the logical rules. Okay? So this becomes, put not f here, and when you say x1 is 1, that becomes x1 implies f, and this becomes f x1, and so on. And here, so you just do that all the way down. Okay, so all these queries just become so this is an application of the cut rule on this formula. Okay, to go from these two to this one. Okay, and at the leaves, where you had a truth table contradiction, here we had a truth table contradiction to f. Over here, remember what f is. F looks like, all of these things, which you can apply the or right rule, and to get rid of these ors, because it's on this side. So this is the same thing as x1, comma, x1, x2, comma, whatever the last one is, x5, and then we still have this x1 here, right? And then you just move that to that side and you get. Okay, so whatever the formula is that you labeled this with, you got a truth table contradiction, very small amount of manipulation will get you, applying, again, the rules in reverse, will get you to f implies f, or in this case, one of the terms in this implies. So in this case, we get x1 implies x1. Does that make sense? So again, a high level is these things, everything you query becomes a formula. On this side, you put it on the left. On this side, you put it on the right. And then to derive, and then you apply the cut rule to get this from those two. Keep doing that. And at the leaf, the claim is, since you have a truth table contradiction, this is a truth table contradiction to just one or and or negation gate. So that's why the proof is so small here, because it just has to use the logical rules for that or. And in this case, we just use the logical rules for that or. Okay. When we get to the one that would violated this one, here we would only have to use the logical rule for the and so on. Okay.
Another question, this is maybe not a representative sample, but I feel like we've used those rules in reverse more than we've used them in the right way. So why do we state them this way?
Just because people tend to think of a proof starting from the axioms and going to the, yeah, it's just a history, I guess. Yeah. And then the other direction is, this takes some manipulation, and you have to see, you have to do a couple things. So first, you have to show that any PK proof can be made tree-like. So by that I mean, if I now I'm going to do the proof in the right direction. So here's the axioms up here. Okay, and then I'm deriving things, right? And this proof, I didn't say that if you view it as a directed acyclic graph, it doesn't have to be tree-like, right? I was allowed, if this was a sequent here, I was allowed to use it more than once. So if you view it sort of as a DAG structure, it might not be tree-like. But it's very easy to convert a DAG-like proof into a tree-like proof of basically the same size. And it's just a trick. It's going to increase the depth of all of the it's going to increase the depth of all of the depth of the whole. So there's two notions of depth here. One is the depth of the underlying, the maximal depth of the formulas in the proof, and the other depth is the proof depth. Okay. So to make this thing tree-like, basically all I'll do is instead of deriving inductively, instead of deriving a line, I'm going to derive the semantic equivalent of the conjunction of all the lines that I've derived so far. Okay. So like if the proof was like, you know, F1 up through Fm, that was the original proof. For each of these is a sequent. Okay, so this would be like, you know, F1, F2, F3, F4, F5, F6, F7, F8. Instead, I'll derive F1, F1, and F2. So I'll just keep all the formulas that I've derived in that step. So that's going to mean that I won't ever have to, you know, I can always just use the previous one to derive the next one. Okay, so that's how you make a proof tree-like. And then once it's tree-like, you can make it balanced. And by that I mean, you know, the proof now is going to look like, you know, F1, whatever. It's going to look like this now. It's going to have that structure, like long and skinny tree-like, but now I can make it balanced. Okay. So I can make it still be tree-like and have depth logarithmic of the size. Okay. And once it has that nice form, tree-like balanced, then it's not too hard to see that even if these rules weren't all cut rules followed by at the bottom by the logical rules, that then you can manipulate it to be of that form without too much trouble. Okay. So let's take a break. 5 minutes, is that good? Circuit families. So I already did unbounded fan-in formulas, and again, you can add a new gate like a mod 2 gate is like a mod 2 connective, and then you can add rules for introducing it on the left and the right, and then you have an equivalence between what's called, you know, Frege proofs with mod gates and bus-Pudlek games over the same thing. So I wanted to say a few words. I won't have too much time. I think I'd like to get to the algebraic proof system, so I'm not going to spend too long on the duality or the model theoretic view of these proof systems, but I want to at least say something. So first of all, I want to say that there's these proof systems. They're purely Boolean, but they really are non-uniform. You should think of them as non-uniform versions of restrictions of piano arithmetic, where induction is restricted to, you know, polynomial time functions or functions computed with polynomial size circuits and so on. Okay, and S12 is like the sort of the most basic of these bounded arithmetic systems. Introduced by Sam Buss, but there's a long history behind it. There's an equational version of it by Cook from the 70s called PV. But S12 is nice because it really looks like piano arithmetic, if you know what that is. It's like the most standard system for first order reasoning about arithmetic plus times and so on. But the induction is restricted to be induction over just on polynomial time predicates. So I'm not going to get too into it, but I do want to just explain that it's very natural, and you can generalize the propositional sequent calculus PK to the first order case very naturally. So you have to, first of all, the setup's totally different. You're in this first order setup now where you have, you know, your model is, you have some underlying universe, and you have variables, some function symbols. You know, typically this would be like plus and times. That would be representing like plus and times and successor. And predicate symbols like less than or equal typically. And first order formulas, you know, you have terms. Terms are either variables or they're built up by applying functions. So this would be like a unary function. This is each function symbol has associated with it an arity. So like plus is, you know, a 2-ary function, and whatever. And successor is a unary function. So terms are, you know, built up recursively, again, starting with variables and applying function composition to, you know, functions of functions and so on. And formulas are, you know, you can apply a predicate a unary predicate to a term, k- ary predicate to k terms, and so on. If you already have formulas P and Q, P or Q is a formula P and Q, not P, and then you can quantify for all xp, there exists xp. Okay, so you're in the sort of language, you're in the world of first order formulas instead of propositional formulas. The only change to the sequent calculus is that you have to have rules now for introducing exist on the left and on the right, and for all on the left and the right. And you can think of exists as really just a huge for all, a huge or, and you can think of for all as just a huge and. So the rule is just, the rules are like, so you have like exists x on the left. Let's make sure I get it right. And on the right, it would look like a of term. Sorry. So this is just a, I call it b. This is just a variable. Okay, it's just called b here because we want to point out that it's free. It's not quantified. Okay, so if you have a of a free variable, that's the same thing as saying there exists an ax on the left. But this is the more natural one. If you have proved a for some term, okay, this means a is true for some universe element, then that means there exists an x where a is true. This is x. Okay. So this is like, a is true somewhere, so there is some value where it's true. Okay. And again, you have similar rules for all on the left and the right. Okay. So you work with this now instead of, in the first order case, you work with this instead of, you just add these, and pretty much everything else is the same, where now you're interpreting the sequence as being first order, sequence is a set of formulas implies a set of formulas, so nothing else has changed. And the only thing that changes about completeness, this is the beauty of it, really. So for first order completeness, sometimes it's very difficult. But here, really, all you have to do is the same proof that we did. So you start in reverse, right, with the thing you want to prove. Now, the only thing is sometimes you don't satisfy the inversion property. Like here, this is a specific term, right? So if you know that there exists an a of x, and in reverse, you want to plug in a of a term. The problem is you don't know which term to plug in. Okay, so this doesn't really satisfy inversion. But the way you get around this is you just sort of like you have to basically keep doing it over and over again until you finally get a implies a. So it's not a it's not a procedure that's always going to necessarily halt. Okay, but if there's a valid proof, it will halt. So you have to enumerate over all terms, and then you also enumerate over all formulas. And in the procedure, when you're deciding what to break up, if you decide at the point in time to break up the exists, in reverse, you're going to pick a term, okay, out of your enumeration of all possible infinitely many terms. You're going to pick one and put it in there, and you're going to keep a up there because you might have picked the wrong one, so you might have to repeat it. Okay, so it's like, so it's it's an enumerable procedure, but it's not necessarily going to terminate. So you terminate at any leaf whenever, again, if you have an a on the left and an a on the right, and you make sure that you do this process so that you'll, if this is true, then you'll eventually get the right term. Okay, and so you can prove the proof is a little bit harder because you have to, again, you keep doing this process. Right, and the only thing that's weird is the exists on the right. You have to repeatedly try different terms, and for the for all on the left, same thing. You have to repeatedly apply, try all possible terms. So you'll be building this tree, and in the case that the formula that you started with at the bottom was valid in the first order sense, then eventually all of the nodes at the top will have you'll eventually be able to stop. So a formula will be, a sequent will be non-active. It'll stop being active. And it stops being active when you have an a on the left and an a on the right. So basically it's an axiom, okay? And so that's the whole procedure for completeness. And then you have to prove that if the process doesn't terminate, okay? then it must be the case that there's a model. And what you do is you use Koenig's lemma, which says, if process doesn't terminate, then the tree is, and when you go to infinity, the tree is infinite, so that means that there's an infinite path. And then you actually can look at all the terms on the path and construct a model. It's called a term model, using those terms and using the values that they're given on the functions and the predicates going up. And you can use that path and what's the terms on that path to construct. That'll be more or less be your model, where the bottom thing will be false. Okay.
This must be something. So like PA is an example of this.
Yep.
Right. So
No. So far I didn't do PA yet. So PA is where you also have axioms and rules that. So right now this is just pure first order logic. I'm not trying to interpret the function symbols. So PA would be this, except that we would also have like some axioms for plus and times, and we'd have induction.
okay.
So then you would need a slightly stronger form of completeness, which would say, if you can prove something from those axioms, if something's valid, you have to do it with those axioms there. The proof is more or less the same. It doesn't change too much.
The completeness. Okay.
Did that help?
So it's
So I think I know what you're. So yeah, completeness.
Well, it has to do with what. Yeah. So what?
So completeness means that if there's if it's true in every model, then you have a proof. So in Peano arithmetic, that would mean every possible universe and interpretation of the functions and predicate symbols. If you can conclude this from the axioms of Peano arithmetic in all these LK axioms, if you can conclude the bottom thing, from those in every model, then it has a proof. So it doesn't violate incompleteness. Incompleteness is saying that the true model that you're intending to model, which is the model of the natural numbers, where the function plus means plus and times means times and so on. Incompleteness is like saying that you can't rule out the non-standard models. Sorry, I'm going astray here. But
Okay.
so if you want to prove a lower bound, so one thing I wanted to say, even though I'm not going to define it, but I could do another lecture if somebody's interested. So again, S12 is this subsystem of Peano arithmetic. There's built function symbols, plus, times, successor, a few other ones, and you have induction. So you have some basic axioms that are just axioms, more or less, that are kind of the obvious ones for these functions, for plus, times, and successor. So they say like, A plus B plus C is A plus B, associativity, all the kind of normal, natural things you would try to do to axiomatize these things. There's just, I don't know, maybe 20 of them or something. And then induction is, saying that if A is true at 0, and it's actually for S12 you have a slightly different form of induction, but normal induction would be like for all x, if A of x implies A of x plus 1, then for all x, A of x. For S12, the induction is a little bit different than this because we want it to be fast induction. So it actually ends up being induction on the length of x. And also you restrict A to be of a particular type, so that you're really talking about just polynomial time predicates. So it'll take a while to explain all the details, but it really does exactly correspond to the uniform version of extended Frege. Extended Frege is the game where the queries are allowed to be circuits instead of formulas. Okay. So just like you might think of AC0 circuits is a non-uniform, well, let me do a better example. Polynomial size circuits is like the non-uniform version of polynomial time. In exactly the same way, S12 is the uniform version of extended Frege. Does that make sense? So extended Frege, you're allowed to query, arbitrary functions that are computed by, circuits. So think of a game as a game that has logarithmic depth. An extended Frege game would have logarithmic depth, and the queries are allowed to be polynomial size circuits. Okay? So that's like a non-uniform proof system where the reasoning is like polynomial time circuit reasoning, and S12 is exactly the uniform version of that. By uniform, I mean if you have like Pigeonhole Principle is really a one statement for every n. You know, there's no mapping from n plus 1 to n that doesn't map two things to the same whole. It's one statement, and we turn it into, you know, a bunch of different statements, one for every n, when we make it propositional. Okay, and if you, whatever it is that you can prove in S12 of that type, where you can express it propositionally, the proofs in S12 exactly correspond to the extended Frege proofs of the propositional version. Okay. In the same way as you can have a polynomial time algorithm for a function, and then you break it up into inputs of length n, and that gives you a bunch of different circuit classes. Am I making sense? If not, you should ask me questions. This is.
So, like, what's something that's provable in PA but not in S12?
Oh, yeah. So that's a very good question. So, so you can use, you know, the Gödel's incompleteness theorem holds for S12. So you can prove like that PA can prove consistency of S12, but S12, or consistency of whatever. But we don't know for statements that are sort of bounded, where you can express them propositionally, one for every n. We don't because S12 is like the uniform version of this, we don't have any examples of those types of statements. So statements that you could write propositionally if you wanted to, we don't have any examples. Yeah. So it's kind of similar to how, you know, for Turing machines, like once you get up beyond polynomial time, it's easy to show that there's functions you can compute, you know, with, you know, there's functions you compute with a Turing machine, but not a polytime Turing machine, using diagonalization and so on. But once you get to like polynomial time and NP, once you get in those low levels, we can't do that anymore. It's kind of similar to that. So anyways, I wanted to mention this because I think that it's important. So the nice thing about the uniform version is there's, you know, there's all this model theory that goes along with it. So there's a complete kind of characterization of when something does and doesn't have a proof in S12. So you have this, you know, this, what we were talking about before. So you know that if something doesn't have a proof in S12, then there's a non-standard model where the statement is actually, you know, false. So for example, for the Pigeonhole Principle, so the way you would formulate the Pigeonhole Principle in S12 is you would sort of think of the function as being some arbitrary polytime function trying to map n plus 1 to n, and then you'd be saying that it can't map it 1 to 1. Okay, and we don't have a proof that that's not provable in S12, but if we did, I mean, because it is provable in S12, but I just want to give you as an example, if you could prove if you proved a lower bound for some system of bounded arithmetic for the Pigeonhole Principle, you would be constructing a non-standard model where there was, you know, a non-standard model where n is infinite, where there is a 1-to-1 map from n plus 1 to n. Okay, but yet in that same model, all the axioms, the induction axioms, and so on of the system are still satisfied. And that's exactly how I-Type proved his lower bound for bounded depth circuits. He looked at the restriction of S12, like loosely speaking, the version of the bounded arithmetic version of the game played on bounded depth circuits, and he constructed a model where the Pigeonhole Principle was, you know, was false, where there really is a map from n plus 1 to n for n infinite, a non-standard model where, you know, all the axioms of the corresponding uniform system were satisfied, but the statement was false. Does that make sense? And I think it's like you kind of, and it's an equivalent, so you kind of have to do that to get a lower bound. So I wanted to talk a little bit about algebraic systems, which I think maybe you'll be more comfortable with. So I'm going to switch gears and talk about those for a little bit. But I'll just mention a few open problems here first. So one open problem is beat, you know, 2 log n depth bound for, you know, bus-Pudlett games. Applied to circuits, applied to formulas or circuits. And I just don't know why this should be hard, to be honest.
Any candidate formula?
Any candidate formula.
But is there anyone that people think is going to be easier to get large lower bound for?
I think almost anything non-trivial like the pigeonhole should require. I mean, this is kind of, again, this result is not really based on anything having to do with the formula being hard, just the fact that it's nested. So that we don't have any argument that's sort of, we don't know how to. So let me give you an analogy. So we know how to get n squared formula size bounds for parity, and we know how to get n to the third formula size bounds for other functions, and those really do delve into the properties of parity or the other function, the Andre function. Likewise here, you'd think for pigeonhole, you'd have to get into the proof would somehow have to say something combinatorial about counting, and that should give you something like n to the third or n to the 3 log, 5 log n something. I don't know if I answered your question, but let's see what other.
Look at some Ramsey kind of statements.
Yep, those would be great too.
We don't have log n depth BP games for like Ramsey theorem.
So people have studied Ramsey theorem statements in their proofs a lot with respect to like resolution, which is loosely speaking. So it's like the bus-PUD-like game where you're only allowed to query variables, except that it can be DAG-like. I didn't define DAG-like because for strong enough systems you don't have to ever look at DAG-like. But for resolution, this trick of converting it to tree-like doesn't stay in resolution. So a bus-PUD-like game for resolution is like a read-once branching program that's finding the contradiction. So you're querying variables. And anyways, people studied Ramsey theorem in that context and have lower bounds there, but nothing for. So the biggest open problem is to prove AC0 to Frege bounds, and this is bus-PUD-like games where the queries or the prosecutor are bounded depth formulas with mod 2 gates and or not mod 2 gates. Okay. And this is particularly frustrating because we know how to prove very strong lower bounds for this circuit class since the 80s. And we don't have any idea how to prove even depth 2 AC0 to the corresponding Frege lower bound, even for the depth 2 case. So it's quite frustrating. And again, there's really nothing, the whole motivation for the algebraic proof systems, I think they're natural in their own right, but the whole motivation for them was really to study the restricted version of this, like the depth 2 version of this. And so that'll lead me into the next part. And then lastly, this is a problem that Jan Krejcik and Sasha Razborov have been talking a lot about, they've been processizing or whatever, is to prove some conditional, basically any conditional lower bound, for either the formula game or the AC02 game. And by conditional bound, we know that if NP doesn't equal co-NP, then obviously all of these proof systems, every proof system is not polynomially bounded. So by conditional, we mean something other than that, something weaker than that, or even independent from that. So there's we have no evidence really of any kind.
Any candidate?
Yeah, the candidates are hard to come by actually. So for so candidates. Let's do for formula game. That's the standard one. That's Frege systems. So there the candidates are. So you can actually formulate consistency in a propositional way for extended Frege. If you think extended Frege or the game on circuits is stronger than the game on formulas, you can formulate a particular tautology that's sort of expressing some kind of consistency of extended Frege. And we know that if there's a difference between those two, then that formula should be hard for Frege. So it's like a complete tautology with respect to Frege and extended Frege. So that's one candidate. It's really hard to work with. another candidate, which is much nicer, but not much is known about it, is basically one-way functions or pseudo-random generators. So you take some function that's, you know, whatever, from 2n to n or something like that. So some function that you think is like one way. So in other words, it's easy to compute in this direction and very hard to compute in the reverse. And you write a tautology, you write a formula where you think it's you write something that says that something over here is not in the range of the function. Okay? And if you think that the function's one way and it's not invertible, you probably should also think that it would be hard to prove that any specific guy on the right doesn't have something mapped to it. Okay, so that's a good candidate, but again, we don't have any idea how to prove such lower bounds. And then other examples, which also aren't very convincing, come from linear algebra. So like we know that like determinant and matrix inversion, all of that requires quasi-polynomial size formulas. So therefore the analogy is that, okay, if the formula is required to do those things is quasi-polynomial size, and if you can concoct some tautology that's not, you know, that's polynomial size, where you think that the only proof of it would require some matrix inversion or some determinant, then you would conjecture that that would also be quasi-polynomial. So for example, you can say, like, if A, B, take a matrix A and a matrix B, both n by n, and say if AB equals I, then BA equals I. And you know, where I'm thinking of this is over like mod 2. So here's an simple example of something you can write down as a tautology. You have variables for, you know, all the matrix entries. Okay. This isn't great because we do have quasi-polynomial upper bounds. So these you'll never get better than, you know, a quasi-polynomial lower bound. But I would guess that these would be the easiest to say. Of all of these, to me, these seem like the easiest ones to prove something, maybe up here. And that's it. There's really nothing, there's really not much else that I know of. I mean, there's other similar types of linear algebra statements. Yeah, I won't get to the lower bound I was going to show you, but I'll at least mention a little bit about so I want to mention a little bit about these algebraic systems. So you guys might have heard of some of them, SOS. How many people know about SOS? Some people? Okay, so the algebraic proof systems, there's two types. There's the algebraic ones and then the semi-algebraic ones. The algebraic ones, you're starting with the you kind of start with a bunch of polynomial equations over some field. Let's say over some field. It doesn't matter. It could be GF2, but we usually think of, and these are low degree typically, and the underlying variables are like x1 through xn, just like before. And we're really, mostly we care about the Boolean case. So we mostly care about, we're thinking of this as I'm going to be thinking of this as a special case of AC0, you know, AC0 2, so, or AC0P Frege proofs. So I'm trying to think of this as a special case of that. Okay, so I'm usually viewing these PIs. So if I start with, so I'm going to switch a little bit, and now I'm going to think of F as unsatisfiable. So so far, historically, when people talk about proof systems in the standard case, historically they usually think of F as being valid. In the algebraic setup, it's somehow historically more natural to think of F as being these as being unsolvable. So you would start with an F that's unsatisfiable. So it would be a conjunctive normal form. It would be like the negation of the DNF. So you'd have a bunch of clauses, you know, C1 and Cm over x1 through xn, and you can convert them to a polynomial equation. So if C1 is like x1 or x2 or x3, it converts to 1 minus x1, x2, 1 minus equals 0. Did I do that right? Okay. So in this way, we can convert an unsatisfiable Boolean formula to a system of polynomial equations, and then we usually also add. So we almost always, if we're interested in the Boolean case, we'll add these equations, xi squared minus, basically to force the variables, try to force them to be 0, 1 valued. Okay. So that's the setup that you start with. And we want to try to prove now that this is unsolvable over this field, and more specifically with these equations over 0, 1. Okay? And so, a special case of Hilbert's nullstone sets, says that, in general, if you have a bunch of equations that are unsolvable over an algebraically closed field, if and only if one is in the ideal generated by the polynomials. In other words, if and only if there exists other polynomials q1 through qm, so that the sum of pi qi, say, is 1. Okay, and since we added these, we can assume that all of this stuff is over the finite field. I'm thinking of this as a finite field. It's like GF2. And since we started with these, we can assume that all of these polynomials, not just these, are all over the finite field. Okay. People look confused.
This is over C, right? For example.
No.
Right-hand side.
The normal null sets is over some algebraically closed field. So I'm saying if these include the xi squared, if these are actually over a finite field, say f, and we include these axioms among these, then you don't ever need anything beyond the coefficients of everything can be in the field.
Just the place
Yeah.
Degrees, yeah.
No, but also maybe we could talk about it offline. It needs a little argument, but I'm forgetting it at the moment. Okay, so this is going to be called a null sets refutation of these over the field F. Okay, and the measure that we usually care about, one measure, is the degree. So the null degree of this, let's call this whole family P, which always include. When I write P, I'm usually thinking of these as being the conversions of the clauses of an unsatisfiable formula together with these xi squared minus xi. But it's interesting, even, if you leave these out, then you're in the traditional setting of algebraic geometry. And if you put these in, and these aren't from, an unsatisfiable formula, it's still quite interesting. Okay. So, anyways, the null degree of this is, is the minimal degree of the QIs that refute this. Okay, so I think of this, this is one particular way to view one as being in the ideal generated by these P's, where I kind of just write it all out, term by, I just write all the Q's like in long form. Okay. So another way I could do it, which has a new name, called IPS for ideal proof system. Another way that you could measure the size of this proof is you could start with, you could think of it as like an algebraic circuit or an algebraic straight line program that starts with the PIs. Okay. So in other words, you could actually, you're trying to construct a one in the ideal. So you start with the P's, and you're allowed to, multiply P's by each other, add P's, right, to eventually get one. So I could also think of the size of the algebraic circuit, the size of the circuit that generates one in the ideal of the P's. Does that make sense? So IPS does a little bit more. It's even a nicer definition. Okay, so that definition, I'm not even going to write it down. It's a little bit ugly because it's still a proof, right? So the proof is going to be, the bottom of the proof is going to be the PIs, and then a line, and then a proof is going to be a sequence of equations where the last one should be 0 equals 1. The initial ones are one of these, and then the new ones follow from two previous ones by either multiplying something by something and multiplying a previous one by something, or adding, or taking some linear combination of two previous ones. Okay, so it's like a proof system in the traditional sense, but you measure the size as the circuit size or the formula size. Okay, now how do you verify that such a thing is a proof? You have to actually be able to verify that it's computing the identically one polynomial. Okay, and that's why you're outside the Cook-Rekau proof system, because we don't know how to do that at the moment in deterministic polynomial time. So we have randomized algorithms that can check if a circuit is computing the identically one polynomial. You with me? Okay. So, but IPS is a slightly is a nicer proof system. It's where you can actually view these objects as circuits instead of proofs. So, and that's what makes them nice. So, I have 10 minutes. I don't know what to do. Let's see. Yeah, let me just finish telling you about it. I'll just stop whenever I have to stop. So an IPS proof, so the motivation is that, so let me call this a Hilbert style certificate. This is what I just described. So it's a proof where the lines are polynomial equations. Each one, it's a sequence of polynomial equations. Each one is either in the initial set or follows from two previous ones by multiplication, so I can take a previous PI and I can multiply it by, by an X, and then, or I can take linear combinations of previously derived ones, okay, and then the circuit that's computed at the end should be the identically one polynomial. Okay, is that good? Okay, so what we wanted to do for IPS is we wanted a definition of a proof that was just a circuit, didn't have this like syntactic rule-based feel to it. So an IPS proof is just an algebraic circuit. Okay, so an IPS certificate for this, unsolvable system of equations is just going to be a single. Think of it as an algebraic formula or an algebraic circuit, and it's going to have two types of variables. Okay, X are the original variables that underlie the P's, and these are going to be placeholder variables, one for each one of these. So there's going to be m of these variables, okay, and n of these. Okay, and what we want to say about this circuit is that we want to force it to be, a legal certificate, meaning it's going to be a witness that one's in the ideal generated by the P's. Okay, so in other words, what we want is when you plug in the P's for the Y's, okay, what should you get there? So when we plug in the P's for the Y's here, we want to actually get the identically one polynomial. And on the other hand, we don't want to do stuff that you're not allowed to do in the ideal. So we want to make sure that when you plug in, and let me just write it down. So that's what I already said. And two, we want to make sure that you don't do anything illegal, because you had these as part of the input before now. So we don't want to do anything illegal. So here we want to say that when we plug in 0 for all the Y's, we should get 0. Okay. This is going to make sure that that I'm really constructing something in the ideal generated by the P's. Okay. Now what's nice about this is just an ordinary circuit. Okay. And these two tests are both, they're both just polynomial identity testing. So this is a circuit, and we want to know if it's identically 1, and this is just another circuit, and we want to know if it's identically 0. So this is just, again, it's nicer than this because there's no rules to it. That's why we call it the ideal proof system. And these can be checked in, just as well as this in probabilistic polynomial time using Schwarzschild. Okay. So this proof system is very strong. It can simulate extended Frege. You can put restrictions on the circuit, and you can put the restrictions that it's bounded depth, just like we always do, and then you can try to prove lower bounds in that restricted setting. But one thing that's really nice about this system is that we can prove that if you could really prove lower bounds for this, superpolynomial lower bounds, it implies that VP doesn't equal VNP. So it implies Valiant's conjecture, that the permanent's doesn't have small algebraic circuits. So it's an even harder problem, but at least we're able to tie some proof system lower bound to some circuit lower bound, which wasn't known for any of the Boolean systems. I think I'll stop there because I probably overloaded you. I was going to tell you about SOS, but it's I've given you too many definitions already.